Hi everyone, thanks for being here. My name is Sunwoo Park and today I'm going to talk about something you've probably heard about vibe coding. We will spend the first half of presentation looking at what vibe coding actually is, why it suddenly became sorry. Yes. And why it suddenly became such a big deal and what its real strengths and weaknesses are. Then in the second half, we will get hands-on. I will show you in the simplest possible way how to set up your own coding environment with Cloud Code, what files like cloud.md and skill.md actually do, and when you would be writing them. Today's goal isn't to make you experts, it's just to make sure these terms actually make sense to you instead of sounding like buzzwords. So please listen comfortably, not heavily. Then let's get started. So what actually is vibe coding? The term was coined by Andrzej Karpathy, a well-known AI researcher. In February 2025, he described it like this. You talk to the AI in plain English, describe what you want, and just let it write the code. You don't read every line. If something breaks, you don't debug it yourself. You just paste the error back and let the AI fix it. He half-jokingly called it forgetting that the code even exists. Compare that to traditional coding, where you write, understand, and are responsible for every single line yourself. Vibe coding flips that. Your job shifts from writing code to describing outcomes and judging whether the result feels right. That's really the code idea, coding by conversation, not by a typing syntax. Then, why did this idea take off so fast? A few things lined up at once. First, the tools have finally become genuinely usable. You probably remember the days when models like GPT or Gemini would answer the first information and spit out broken snippets of code. Those AI models have now advanced to the point where they can actually build working applications, and new tools like Cloud Code or Codex let AI go beyond simply suggesting text. They can directly execute commands, modify files, and execute coding. Second, the barrier to entry has collapsed. People with zero coding background like designers, students, and more have actually started building working apps. Third, this spread not as a technical spec, but as a story. For example, a tweet saying I knew nothing about coding and I built a working app in a single weekend is really compelling, and it kept going viral throughout 2025. When these three things, better tools, a lower barrier to entry, and a compelling story come together, it is not being just a technology, but it becomes a movement. Then, next, let's talk about vibe coding's advantages and disadvantages. First, speed is the obvious one. Going from an idea to working demo can take hours instead of weeks. Second, it dramatically lowers the barrier to building something. You don't need a few years of training to test an idea anymore. Then it's especially great for throwaway work, quick scripts, internal tools, hackathon projects, things where perfect code quality was never really the point. And even for experienced developers, it removes a lot of tedious and repeatedly tasks and freeing them up to focus on the parts that actually need human judgment, like on architecture and design decisions. In short, for prototyping and exploration, It's a really powerful shift in how fast ideas can become real. But there are also exists the other side. The biggest issue is that AI written code can look correct while quietly being wrong. It compiles, it runs, it even passes a quick glance, but the logic underneath can be subtly broken or insecure. That creates a review bottleneck. Someone still has to check the work, and reviewing AI generated code turns out to be its own skill, different from reviewing a colleague's code. There's also a there's also a quieter risk. If you never read what the AI generates, you can lose touch with your own code base. And that's especially risky for people early in their careers who are still learning to debug. So the honest summary is it's fantastic for prototypes and exploration, but risky if you skip the review step and push it. That actually matters. Then, so how do you get the speed of vibe coding without the risk? This is where harness engineering comes in. Think of the AI model like a powerful horse. The power is the horse's power is immense, but there's no direction. A harness is the structure around it that decides where the power actually goes. Same idea is harness engineering. The model itself barely changes, but what you build around it changes everything about how safely and usefully it behaves. There are really four simple pieces. First, context. What the model actually knows, like your files and conventions. Second is tools. What it's allowed to do, like editing files or running commands. Third is a feedback loop. How it checks its own work, its own work through tests or running the code. Finally is guardrails, the boundaries on what it's not allowed to touch. Get these four right, and vibe coding stops being risky and starts being a real workflow. That covers the theory. Now let's actually build one in the simplest way possible. But it means rather than writing the code now, I will just give a brief explanation of the environment setup. I will be basing the explanation on Claude Code as the AI tool. And first, I'd like to share a well-known analogy. Imagine Claude is a smart new teammate joining your project on day one. What would they need from you? First, instructions on how your project actually works. That's what Claude.md is for. Second, a manual for specific, repeatable tasks they will do often. That's skills.md. And third, access to any outside tools or systems they will actually need, like your database or GitHub. That's what MCP handles. That's really the whole mental model. Let's go through each one. First up, Claude.md. This is simply a markdown file sitting at the root of your project, and Claude reads it automatically at the start of every session. No need to paste it in yourself. So what goes in it? Basic things, your coding conventions, how your folders are organized, the exact command to run tests or start the build, and anything you specifically don't want Claude to do. When should you write one? It's right when you start a new project or the moment you notice you're repeating the same instruction and in your prompt. That's your signal to move it into Claude.md instead. And keep it short. This isn't documentation for a human leader. It's a quick briefing. A few clear bullet points beat a long essay every time. So update it as you go, whenever you notice Claude keeps making the same mistake. Next, skill.md. If Claude.md is general background knowledge, a skill is a specific packaged how-to guide for one repeatable task. For example, how we write database migration in this project, or how we format our weekly report. It lives in its own folder, and Claude automatically loads it only when it's relevant to what you asked. When do you write one? Not on day one. Write skill after you explain the same multi-step task to Claude 2 or 3 times and realize it's a pattern worth saving. The one gold rule is one skill, one job. Don't cram 5 unrelated tasks into a single skill file, or it becomes unreliable about when it should trigger. And write a description, write a comment, telling Claude exactly when to use it. That description is literally what decides whether the skill fires at the right moment. Third, MCP, which is the Model Context Protocol. This is the standard way to connect Claude to things outside your local code base, your GitHub, Slack, or a database, Google Drive, whatever tools your actual workflow depends on. Think of it like giving your new teammate a key card to a specific room in the building instead of them having to guess or ask you to fetch things manually. When do you set one up? Only when a task really needs something outside your files, like currying a live database or reading a shared document. For a beginner setup, recommended advice is don't connect everything on day one. Start with nothing or just one connector you know you will use, and add more only when you actually hit a wall without it. Over-connecting only just adds noise and risk for very little benefit. Then put those 3 pieces together, and here's what a minimal, real project looks like. At the root, you have your Claude.md file. Inside the hidden .claude folder, you have a skills directory. When each skill gets its own subfolder with its own skill.md, and if you've set up MCP, that configuration usually lives nearby too. Everything else is just your normal source code. That's finished. This is the whole harness from part 1. Made concrete, Claude.md is your context, skills, and MCP are your tools, and running your test is your feedback loop. Notice how small this is. You really don't need anything more complicated to get started. Then with the structure in place, day-to-day work follows a simple 3-step loop. First, explore. Claude reads the relevant files and makes sure it actually understands what you're asking before touching anything. Second, code. It writes or edits the actual files. Then third is verify. It runs your test, checks the output, and confirms the change actually works, not just that it looks plausible. Then it repeats as needed. This is the same feedback loop concept from part 1, just in action. And here's the one habit worth building for yourself. Don't skip your own final check. The loop makes Claude verify its own work, but you are still the one deciding whether the result is actually right for your project. Here is a few practical tips before you try this yourself. Start with just Claude.md. Don't build skills or connect MCP servers until you actually feel the need. Adding structure too early just creates overhead with no payoff. and write your instructions the way you'd brief a new hire in plain language, not like you are programming a machine. Then always read the difference before you accept a change. You can sure buy, but verify every single time, especially early on while you are still building trust. And start with small tasks. Let Claude on bigger responsibility gradually, the same way you trust a new teammate more over time, not on day one. Let's wrap up with the key points. Vibe coding is just describing what you want in plain language and letting the AI write the code. It's really powerful, but it needs structure to be safe. The structure is what we call the harness. And building that harness is simpler than it sounds. 3 building blocks, Cloud.md, Skill.md, and MCP. Start small, only add pieces when you actually feel the need. And always keep your own judgment in the loop. That's everything I wanted to cover today. Thank you for listening my presentation.
Following Following the first present, I will now present the second part of the survey. This presentation focuses on ontology and knowledge graph technique for AI coding agent. Traditional coding is synthetic centric. Developer manuals write coding using an IDE and compiler and debugger. In contrast, Vibe coding is intent-centric. Developers describe what they want in natural language, and AI coding agent generate code by retrieving the necessary project context through MCP. So what is an ontology? What is in the left picture? Human knows that object is a cat. So we also know that cat is an animal, mammal, and a living thing. In other words, we naturally understand both entities and relationship. However, computers do not understand this relationship by themselves. So previous AI agents repeatedly search the code base using grep and read file to find the information they need. As the code base grows larger, this approach has several problems, including higher token usage or more tool calls and slow response time and repeated searches over the same code. So recently, workflow used by many recent AI coding agents. First, the source code is analogized through AST parsing. Then it is converted into a knowledge graph and stored in a database. And MCP server provides standardized access to this structured information. Finally, agent coding agents such as Cloud, Cursor, Codex, and Winsurf retrieve the graph through MCP instead of repeatedly search raw source code. This enables faster and more efficient code understanding. So our idea is apply the same concept to source code. Instead of treating code as a plain text, we present it as an ontology. Function and class, variable and modules become entities, and their dependency and interaction become relationship. This allows AI to understand the structure of a code base rather than simply reading text. This is AST parsing. The first step is AST parsing. The source code is parsed into an abstract syntax tree using tree shitter. Instead of treating the code as plain text, AST parsing extracts each structural element such as functions, class, import, function calls, and variables. These extracted elements serve as the foundation for constructing the knowledge graph. Next, we build the knowledge graph. Code elements become nodes. Their relationship becomes edges. For example, in function A calls function B, we create a core relationship between them. This graph structure helps the LLM understand and relationship within code base. So this is next component is model context protocol. MCP provides a standard interface that allows different AI coding agents such as Claude, Cursor, Codex, Gemini to access the same knowledge graph. Instead of implementing separate integration for each agent, MCP enables them to share the same structured context efficiently. So why does MCP matter? So without MCP, every model and every tools matches by themselves. So it creates M by M integration problem. But with MCP, models and tools communicate through a single standard interface, so reducing the complexity to N plus M. The next step is community detection. The knowledge graph is automatically divided into meaningful modules, such as front-end, back-end, database, authentication. This modular structure helps the LLM focus on the most relevant part of the code base instead of analyzing the entire graph. Finally, the system uses hybrid search. Instead of relying on a single search method, it combines key search and embedding search and graph traversal. By integrating these approaches, the system can retrieve more accurate and context-aware information from the code base. Finally, these are key findings from paper. First, context engineering is becoming more important than prompt engineering. Providing high-quality context is more effective than simply writing better prompt. Second, MCP is emerging as a standard interface, allowing different AI coding agents to share the same knowledge graph. Third, instead of using RDF or OWL, most recent systems prefer PG, property graph, because they are simpler and more particular for representing code relationships. In addition, code property graphs or CPG are mainly used for security tasks such as vulnerability analysis and patch generation. Finally, the lecture concludes that context is the main bottleneck. Better context improves efficiently, reducing cost by about 35% and token usage by 57% and runtime by 46%. So this lecture introduced 19 projects and 6 categories. The first figure, this figure summarizes the 19 projects surveyed in this lecture. The projects are grouped into 6 categories based on their main purpose. The largest group combines code graph with MCP, enabling AI coding agent to efficiently access structured code knowledge. Another group focuses on graph database, which store and manage knowledge graph. There are also projects for semantic or symbolic agent memory, and security using code property graph. Finally, the paper includes several general graph RAG projects as reference. Overall, the survey shows that recent AI coding systems are moving toward coding knowledge graph and MCP-based architecture rather than relying on raw source code. So we introduce KinNexus. KinNexus is one of the representative projects introduced in this lecture. It uses Presentor to parse source code from multiple programming languages and stores the resulting knowledge graph in KujuDB or LadybugDB. It also combines vector search, keyword search, and community detection to organize the code base efficiently. Its main advantage is deep integration with cloud code. KinNexus, KinNexus can analyze the impact of the code change known as the blast radius with a single tool call. In addition, the entire system can be initialized using a single command and making it easy to deploy. Next is Graphify. Graphify extends the idea of a code graph by supporting multimodal information. It parses source code from 25 program languages and run entirely on local environment without requiring an external database. In addition to source code, it can integrate PDF, image, video, and database scheme and infrastructure files into a single knowledge graph. Another key feature is that it labels reasoning results as extracted, inferred, or ambiguous, making the generated knowledge more transparent. However, because it supports multimodal data, the amount of inferred information increases, which may reduce reliability. Unlike KinNexus, Graphify focuses on building an unified multimodal knowledge graph rather than only analyzing source code. Next is code graph. Code graph is a lightweight code graph system. It parses source code using Presentor and storage graph in SQLite. So no external database or server is required. It also uses recursive CTE to efficiently traverse the core graph. The system provides 9 MCP tools, including search, context, color or query, and impact analysis. So they allowing AI coding agent to navigate and understand the code base efficiently. Compared with KinNexus or Graphify, code graph focuses on simplicity, lightweight deployment, and fast local code analysis. That is, understand anything. Understanding anything focuses on automatically understanding an entire software project. It uses a multi-agent pipeline to scan the project and generate a knowledge graph stored as a JSON file. It also creates an interactive HTML dashboard, allowing users to explore the project structure visually. Its key feature is the guided workthrough and persona-adapted interface, which presents different levels of the detail for junior developer, project manager, and senior engineering. After the project is indexed, the dashboard can be used without additional LLM calls, making exploration fast and cost-effective. The main limitation is that the knowledge graph can become outdated if the project changes and automatic updates are not enabled. Unlikely, KinNexus and Graphify understand anything emphasizes project understanding and interactive visualization rather than real-time code retrieval. So this table provides an overview of the representative AI tools. Although each tool has a different implementation, so they all share the same goals, improving AI code understanding by using structured knowledge graph instead of raw source code. So this lecture's conclusion. In conclusion, this survey shows that context engineering is becoming more important than prompt engineering. Instead of repeatedly searching raw source code, recent AI coding agents build a knowledge graph and access it through MCP. This approach provides structured context, improves code understanding, and reduces cost and token usage and execution time. Overall, knowledge graph and MCP are becoming the foundation of next generation AI coding agent. Finally, this table is provided as a reference. If you are interested in any of these projects, you can visit their GitHub repository to explore the source codes and implementation details. Thank you for your attendance.